continue. So today we're going to talk about topological properties. So I mentioned last time briefly that topology relates to open and closed sets. Today we're going to see some other properties relating to this, which actually relates to open and closed sets a bit as well, but it's going to be a bit hidden. Now, as I mentioned, having a topology course is not a requirement for this course here, but we're going to touch into some of the details, but we're going to take advantage of the fact that matrix groups are in the general space of matrices, which is Rn to n square or Cn to n square. So it can be just seen as a normal vector space. And we'll also see that I was a bit quick with my reply last time, if there are any open subgroups of the general linear group. We'll see here that what I said was last time that if you have an open subgroup, then it's the group itself. That is true for the general linear complex matrices, but I forgot about connected components. So we'll see that there is actually a subgroup in the real general linear group that is open, and that is not actually the full group. So let's look into these topological properties today. So there are three main important things. So call that we have a matrix group that is inside the general linear group that itself is inside matrices of so we're fat K here is R or C. And as a space, this is just K to n square. If you're just taking each of the, so there are n square n square coefficients, and you can consider those by itself. So G is compact if it is closed in and bounded as a subset of the matrices. So if it's a yeah, so if it's closed and bounded, then we say that it's compact, and some things are easier when things are compact. So compact is then the analog of a closed interval on the real line. And from your basic calculus course, you know that a function has always a maximum, for example, on a closed interval. It's not necessarily true for an open interval. And compact set sort of plays the same role in this general setting. For example, we're going to see that if we have a compact group, then we can have a way of defining a volume which is finite, and we can actually do some averaging over compact groups. So let's do some example of groups that are compact. So for example, we can do the orthonormal group. So recall that was matrices such that A and A transposed is equal to the identity. And we could see that as a kernel of a map F, or let's say the level set of F inverse of I, where F was the map from matrices that took a matrix and put its transposed, and this is continuous because it's a polynomial. So almost for almost everything, the answer it's continuous because it's a polynomial, and this is closed because it's a level set. And here, I don't like this map. I can define this map to go from all matrices into all matrices. So it's a closed subset in all matrices. So we have the first part here, it's closed. So we can put a green check mark here. So that's the first part. So what we need to show in order for it to show that it's compact is to show that it's bounded. And the simplest way to do this here is to use that, okay, if we have an orthogonal matrix, then then its columns are an orthonormal basis. Then the length of a square I can see that as the length of every coefficient summed together just in the Euclidean norm, but it is the same as if I were to just take the length of all the columns and add them up. So if I'm doing the sum over I here, I'm essentially doing the length of all the columns. And this is an orthonormal basis, so the length of each of these is 1. So this is n. So for all of these orthogonal matrices, the Hilbert-Schmidt norm is, so A is square root of n. For all in ON. So ON is bounded. So in general, I put perhaps bounded up here and I didn't say what bounded means. So bounded G means that there is some, let's say, small m. Let's put large m, even though it could be confused with matrices, such that this norm is less or equal than m for all A in G. So that's what bounded means, is that in this norm, you can't have an arbitrary large norm. So when we talk about being closed and bounded, what we mean by bounded is that you can't have matrices of an arbitrary size with respect to this Hilbert-Schmidt. So here we have then another green check. So, and then we have, we can write check plus check equals compact. So, okay, that check went really bad like this. So these two properties together means that this is a compact space. And we'll later see that this means that we can average around this space. It means that any function on this space will have a maximum and so forth. I'll pause a little bit. So the complex analog of this, which we didn't discuss last time, which we can discuss now, is the unitary matrix. So what are the unitary matrices? So these are complex matrices with complex values. But rather than the transposed being the identity, we have that A and then this conjugate transposed becomes the identity. So orthogonal orthogonal matrices are the ones that satisfies A x dot A y is equal to ax ay for x y in Rn, and then where this is just the inner product j equal 1 to n x j y j, like this. If we consider Cn with inner product let's call it set, yeah, set W equal to j equal 1 to n, and then you have set, let's say, set j w j, and then you need to put the conjugate on top there. So we have these are like the Hermitian inner product on Cn. If we have something like this, then A in UN are exactly the matrices satisfying a set a W is equal to set W. So in this sense, the unitary matrix are like the analog of the real of the orthogonal group in that, okay, if you consider Rn, let's say this should be Rn, with the usual inner product, then the orthogonal matrices are exactly the ones that preserve this inner product. If you consider Cn with its normal inner product, then the unitary matrix are the one that preserve this. So why? So for the real case, when X is in M and R, then X small x y is exactly X transposed y. And then the complex case, if you want to move this over, it will be exactly this conjugate transposed here. And that's where you get the two identities from. So if you try to put in these matrices, here you will need that, for the complex case, you will need that x star will need to be the identity, and for the other case, you will need x transpose to be the identity. So yes, back to the unitary matrices. So yeah, did I? Yeah. Okay. So see. Okay, I can't write here. Right now I can't. Let's see. I'll try to reconnect. Yeah. Okay. So it's also similar in the sense that if A is in UN, then A can also be written on a form like this, but when now this is an orthonormal basis, in CN. So this you can verify with the same argument, just as the orthogonal matrix consists of an orthonormal basis in Rn, the unitary matrix consists of an orthonormal basis in C. So they are the analog there. And sorry, it's for some reason my pen keeps disconnecting. What's going on? Sorry. Okay, I'll stop my recording a little bit. Okay, so so UN is then an example of something that is also compact. And so it's like a level set of A transpose, of the map, A maps to A conjugate transposed. And you can also check that all of these have length square root of n. So this will then be is also then like a compact group. So there are two examples of this property. So let's look at the next property. definition, Lie group, matrix, sorry, a matrix Lie group. G is said to be connected if for every B0, B1 in the group, there is a continuous curve to G, such that A0 is B0, A1 is B1. So you can also do another interval than 0 and 1, but this is the general idea. Yeah, so the point is, yes, I should probably write something like this. T maps to a T, such that. So if you're doing a topology course, they will call this being path connected, and it's not necessarily the same as being connected, but for all the spaces we're going to be consider, it's good enough. So let's look at two first very simple examples. So the simple examples is consider GL1R and GL1C. So this all invertible 1-by-1 matrices, well, this consists of elements like this, where A is real and A is non-zero. Whereas this consists of all A's like this, where this is complex and non-zero. So for the first one, it's the real line. And the second one is the complex plane. But without 0 here, and then without 0 here. And then for the real line, this one is not connected. So if I have B0 here and B1 here, there is no way I can draw a curve in a continuous way because I can't pass through 0. So this is not connected. Whereas if I'm in the complex plane, this can always work out. So, this is sort of a separation and a way to good way to picture being connected or not connected is this simple one-dimensional case. So this is the easy picture, but actually this works in any dimension. So theorem for n equal 1, 2, 3 general GL and R is not connected, while the complex matrices are connected. I'm going to finish around 5 minutes to 13:05. Since we have some technical problems, I'm stealing 5 minutes from the break, if that's okay. So what is the proof of this? So the proof, let's call this A, and let's call this B. So the proof for A is the following. So if you, it's essentially this thing here. So it's that the determinant is a continuous function. So if A of t is a continuous curve, then the determinant of A of t is also continuous. So hence, if the determinant of B0 is, let's say, since we had it on the drawing, greater than 0, and determinant of B1 is less than 0, then there is no curve A of t from B0 to B1. Because if there was such a curve, then you could take the determinant of that, and then you would have a curve on the real line that went from a positive number to a negative number without actually passing through, without somehow passing through 0, which we know is not possible. So this image still works for the general linear group. You just use the determinant to reduce yourself to that case. And then let's see, do we have time to do B? Let's see. So, okay, I'm going to try to see if we can do B. So it is enough to show that we can connect any matrix B with the identity. Because if I can go from B to the identity, and any other matrix is also connected to the identity, then I can just connect them through going to the identity. So it's sufficient to show that I can connect any matrix. If I show that there's a curve going from any matrix to the identity, then I know that there is a curve connecting any pair of matrices. So, and then I'm going to use a theorem from the appendix. So last time we talked about the fact that, okay, any matrix can be approximated by a diagonal matrix, but in general, matrices are not diagonal, but they can be written in the following way. So we can always write B as C D plus N C inverse. So appendix, then I mean, so let's write appendix A, both in book and in notes. So whether or not you're using the book or you're using the notes, this result is in appendix A. So this is just a linear algebra result that you can write any matrix up to a basis change. It's a diagonal matrix plus a strictly upper triangle matrix. So D is then a diagonal matrix like this. And it will be very convenient for me later to just have the notation that this is the diagonal. I just write this whenever I have a diagonal matrix. I just write this as the diag and just the entries, just to avoid having to draw this every time. And N is strictly upper triangle. So it has zeros here and zeros beneath, and then perhaps something else. So strictly upper triangle. So then I can do step 1, curve from B to C D D C inverse. Let's call that B2. And this curve is just A of t equal to C D plus 1 minus t. And then the N matrix, and then C inverse, where this t is between 0 and 1. And what is the trick when dealing with all of these matrices, right? Because you can connect any matrix to any matrix by just doing a linear interpolation, right? So connecting them in Rn plus square plus 2. But the problem is that you have no guarantee that the matrix will remain invertible if you're doing that interpolation. But like if you have something that is an upper triangular matrix, then for any upper triangular matrix, the eigenvalues is on the diagonal. If the determinant is non-zero, you can do anything with the upper diagonal, the determinant will remain non-zero. And so so we can change this part without risking this becoming non-invertible. So perhaps I should write this. So if I write this as 1 d minus Tn, so that's really the only thing you need to worry about is this becoming non-invertible. So that's a matrix like this with 0 here, and here you have 1 minus t times whatever you had on top. And then you have that the eigenvalues are here. So the determinant here just remains just a product of these things on the, if you have an up triangle matrix, the determinant is just the things on the diagonal. So this will remain, this will remain invertible even with this change of the upper path. So that's the first part, is that we can get rid of this nilpotent part so that we are left with just the invertible part, and then just with the diagonalizable part. And then step 2 is that I can define another curve, a of 2t. So now we're down to this diagonalizable part here. So next part, I can define c d of t c inverse, where a2 of where d of t is the diagonal of, see, I told you it will be useful, of these curves here, where lambda j of t is a curve in c minus 0 from lambda j 0, which was the original lambda j, to lambda j 1, lambda j 1, which is just 1. So again, I'm going, so if you permit, I know you're taking notes, but I'll do a short skip up again. Again, we're just using here that the complex numbers without zeros are connected. So if I have any complex number, I can always go to 1 without crossing the identity. So so that means that for any of these, any diagonal matrix, I can change the eigenvalues in a way such that they never become 0, and such that they go to 1. And so that means that the D at time 1 is just the identity matrix, and that means that A at time 1 is also the identity matrix. And so we are done. So it's interesting that just like for the one-dimensional case, it's not connected when it's higher dimensional for the real case, but it is connected for the complex case. And the reason they are connected is, or not connected, is more or less the same reason. I'll end by one short definition, which is for matrix Lie group G, we define the identity component as G0, any A and G can be connected by a continuous curve to the identity matrix. We will see that G0 is also a matrix Lie group. So the picture you should sort of have is that for GL and R, you have these spaces of positive determinant, which is the G0, which live in their own world. And then you have the one with negative determinant living in their own world. And so these two cannot, so you can't get over from one to the other with a continuous curve. Sure, you can multiply them and stuff, but you just as the positive and the negative numbers, if you remove 0, are not connected, these will not be connected if you remove the non-invertible matrices. Okay, so the next concept we want is definition. So I'll go according to the definition in the book. We say that G is simply connected if it is connected and any loop, i.e. Continuous curve, from 0, 1 to G, T maps to a T. With A0 equal to A1. Can be continuously deformed to a point. So I put the formal definition in the appendix of the notes because it's a bit difficult. Okay, what do we actually mean by continuous deformations and so forward? But let's look at some examples. So if we again look at GL1C, that is not simply connected. So if I have the point here and I have a loop from 1 going around this point, then I cannot contract this loop to a point. So let's see. Let's write here while keeping endpoints fixed. Yeah. You can get around this not being fixed, but it's a bit easier to just because it doesn't really matter. So if I'm so the idea you should think of is that if you're standing in 1 and you're pulling on this rope and you have this rope around 0, and if you're pulling this in, then eventually you will capture 0 and you won't. So if you're doing a deformation here, let's say, then if you are pulling on this thing, then eventually it gets stuck around 0 and you cannot deform it continuously past that point. And so you cannot then deform it to a point. And so you can think of simply connected as no holes. So in a way, that is also why that's how we think of it in the complex analysis courses. We're thinking of it as no holes, and this is kind of true. So let's look at another example. So let's consider SU2. Now SU2 is U2 intersected with SL2C. So it's in other words, it's the unitary matrices, but it has determinant 1. So we looked at last time. We looked at the orthogonal group, which is then the rotations, and then we looked, rotations plus reflections, and then we looked at the special orthogonal group, which is then just rotations. And we talked about the fact that this group has determinant plus minus 1, and so it was really here you're just reducing to the ones with determinant 1. So here is a bit more complicated because if A is in the unitary matrix, then the determinant of A is a complex number of length 1. So the determinant is somewhere on the unit circle inside the complex numbers. So whereas this is basically like the image we had before with two connected components, picking SON, it's just picking the component with determinant plus 1. The unit for the unitary matrix, you have like a whole real dimension of possible determinants, and you're really actually dropping a dimension by restricting to determinant 1. So it's a bit larger restriction for the complex numbers, since you can have, this is rather than just being 2 values, it's actually a full circle of possible values for the unitary matrices. Okay, so this is the formal definition, but you can write them in, if you want to look at them explicitly, you can write them like this. Let's see, I'll just make sure that I'm writing it the same way as as I write them in the notes. So you can write them like this. So they are matrices of two complex numbers given here, such that the determinant is equal to 1. Well, that's just this plus this being equal to 1. So that's how all of the matrices in this group look like. They look, they're given by two complex coordinates who together add up to 1. And so as a space, you can identify that with set 1, set 2 in the complex numbers, so you can look at that as all of the complex numbers in set 2, which has length 1, which you can look at as the 3-sphere inside of C2. So it's all the numbers of all the vectors of complex vectors of length 1, or the real vector. You can look at that as all the real vectors in R4 with length 1, and that's the 3-dimensional sphere. And S3 is simply connected. So this is not a 3-sphere, this is a 2-sphere, but it's not very different when you go 1 dimension up. And then if you have a loop on this this space here, then you can always sort of contract it down into a single point, and that's and you can need to actually check this mathematically for the S3 sphere, that it works out the same way as it works on the 2-sphere where you can draw it. But this is also a simply connected space. So SU2 is simply connected. Now notice that I said before the simply connected is means no holes. So if you just look at the image of the 2-sphere, you could argue that there is some sort of hole inside of the 2-sphere, right? That you have this, that it surrounds something and that there is like a hole inside. But this is not the type of hole that you can catch with a rope, right? So simply connected means a type of hole that you can actually catch with a rope. If you put a rope around a sphere and pull, it will fall off eventually. So we will not deal much with things being simply connected or not being simply connected, simply because, well, we don't have much of the tools to deal with this sort of thing and actually prove things around it. But it's nice. It's very nice if you later in the course understand this concept in a more like abstract sense, at least understand a bit what it means, as it will show up a bit later when we talk about the relationship with Lie algebras and Lie groups. Return again. So next we want to talk about matrix exponentials. And the interesting thing about matrix exponentials is that if they work a little bit like normal exponentials in the real numbers. So how do they, and real and complex numbers? Normal exponential map. So real case, how do they work? So X will then be a map going from R, but it will only hit elements in R plus, right? So it will not hit all of the elements. So, or you can call it the identity component. Of GL1R. So this is the part that contains, there are two connected components. This is the part that contains the identity. It's this one. For the complex numbers, however, the exponential map goes from C into C minus 0. And this covers all non-zero complex numbers. So this is a bit interesting that we have this relationship, because we're going to see this being played out again when we look at general exponential matrices. So if x is in M and K, K is R or C, then we define e to the power x as the sum from m equal 0 to infinity of x m factorial. So it's the same formula, same computation of matrices, and then we have the following theorem. So you have then that x from mapping x to e of x is well-defined continuous map from the all matrices into the invertible matrices. So just like the exponential map here will never give you 0, taking the matrix exponential of any matrix will give you something invertible. Also, it has properties A, that if you take the exponential of 0, you get the identity matrix, which is again true for the normal exponential. If you take 0, you come to 1. We have a somewhat similar relation with addition. So if you add two matrices, then it's the same as multiplying them together. And here I say I have a typo in my notes. Let's say, so this one should also be x. So if you have the same matrix and you'd look at what it means if you add together two constants of that matrix, is the same as multiplying them together. In particular, E of x inverse is equal to E inverse x, me minus x. Which follows from the previous one by taking alpha to be, if you take alpha to be 1 and beta to be -1, this part here would need to equal this, which would be 0, which would be the identity, right? So this, if I take alpha equal to 0, beta equal to 1, then this is the identity. This is e to the x, and this is e to minus x. So hence it has to be the inverse. So next, if x y is equal to yx, which generally does not hold, but for those matrices where this holds, then e to x plus y is equal to ex times ey, or ey times ex. So then if the matrices commute, then their exponentials will also commute, and it will be given by the sum of both of them. So next, the exponential max works very well with conjugation. So if C is a general linear map, can be general linear K, then taking conjugation, it's the same as conjugating after applying the exponential map. And a final property, if I want to take the conjugate transposed, this is the same as taking the conjugate transposed before. So let's see here how much of the proof I'm going to do. Okay, I can do a little bit more. Okay, so see, yeah, we're dealing with this next time. Okay, so let's do the let's do the proof first, so that the mapping is well defined. So here we recall we need to use that x. So first time we showed okay, at the very end of the first lecture, I mentioned that we have the following relationship. For the norm, meaning meaning that we also have then the following relation. So if if I take the sum and look at the absolute value, then that's less or equal than the value of this to infinity. So taking this sum, but with the xn on the inside. What is this? This is just e to the power of the length of x, which is in particular is for one given matrix is less than infinity. Hence, the sum m going to 0 to infinity of x m over m factorial converges absolutely. So what this means is that if we define fk of x to be the sum from m equals 0 to k of m factorial, then x, which is equal to the lim k going to infinity, fk exists, and now let's see, I'll not be that brief because we need okay, let's not use that much pre-requests. Okay, let's give a few more details. Sorry about this. I want to give a few more details. So this converges absolutely. So we consider fk equal m from 0 to infinity xk of m and factorial. These, let's say, sorry, sum to k. So these are continuous because, again, no, sorry, this should not be absolute value. Like this one. So we considered these following functions: f of k, which takes x and takes us some of the first k elements. So this is continuous, again, because it's a polynomial and well-defined. Considering the set of matrices where all of the elements are bounded by R, we see that if I take the exponential and then subtract f of k of x, then I'm having a sum m1 k to 1 to infinity x k m or m factorial, which is less or equal than the sum m k k plus 1 to infinity r n m n, which goes to 0 as k goes to infinity. the consequence Fk converges uniformly to exp on the set x is less or equal to. So from the fact that this series converges absolutely, we have existence. So it's an just with the same proof you have in calculus, if we have a series that converges absolutely, then the sum exists. Then the sum will converge towards a concrete object. Next thing we need to do is to show continuity, and the way we're going to do that is we're going to look at the finite sums, which are continuous, and then we're going to show that if I have an element that's no larger than r, then I can bound the difference between the exponential map and this SFK by something that doesn't depend on x. And uniformly means that essentially that this does not depend on x. And one of the properties of uniform convergence is that if you start off with the sequence of continuous function that converge to something uniformly, then that the final function you get is continuous. So let me just write up this here. Note if f of x converge to f uniformly, and f k is continuous, then f is also continuous. So for this case, this means that exp is continuous on the set r less than the size of x less than r. And since r was arbitrary, so any x is in one of these sets, then exp is continuous. So then again, first we show that this map actually exists for everyone by using absolute continuity of the series. Then we need to show that it's continuous, and we do that by showing uniform continuity, meaning the continuity that over a set that does not depend on each of the elements. And then we use the fact that limits of uniform continuous function, a uniform limit of continuous function is also continuous. Okay, then I'm resuming the recording again. Then we need to prove all of these other results. So we need to prove the A, B, C, D, E results, okay? So that if we take the exponential of the zero matrix, then we get the identity. This is just trivial from the definition of the exponential map, right? All all of the powers higher than 0 go to stop existing because it's a 0 matrix. B, what was B? B was alpha beta x is equal to E alpha x times E beta x. That is a special case of C, which was that if x y was yx, then ex plus y is equal to ex times ey is equal to ey times ex. And then the proof is the same as for numbers. Ex plus y, then is then sum m equal to 0 to infinity, x plus y, m factorial times m. Okay, if we now compute this one in more detail, if we expand this thing here, then this will be then the sum from k equal to 0 to m over k, x k times y m minus 1 divided by m factorial. So that's how you do. That's just a binomial formula for this expansion right here. So, but then what is this expression? Well, this expression m over k, well, that's m factorial divided by k factorial, m minus k factorial. So we can shorten an m factorial upstairs and downstairs. So we get that this is the sum from k equals 0 to m of x to the power k, y to the m minus k, divided by k factorial, m minus k factorial. And then if you just rearrange the terms, you can show, so since we have the sum over all the terms on this form here, you can show that that's the same as just taking the sum of all combinations of m and k, where you have yk, m minus k, no, sorry, y and m here, y k factorial and m factorial. So this is, I think, is the hardest part of to realize is equality between these two. But it's just, if you think about it here, what is this sum? Well, it's actually the sum where all types of combinations where you have k to x to some power divided by the same factorial, y to some power divided by the same factorial. And so if you sum over all of these combinations, that's the same as summing over all of these. And that's the same as looking at the sums of the two series here. The product, sorry, of the two series here. So, okay, here should be K, and here should be M. Ym over M factorial, and that's EX times EY. So it in this way, it's exactly the same as for the real numbers, because the difference in the algebra of matrices and the algebra of real numbers, it's a computation is just this, that matrices don't commute. So if you have that matrices commute, you can do exactly the same algebraic operations. And then we have D, which follows from the fact that if you take C inverse and do it m times, then it's equal to x C inverse. And E is from the fact that if you take the conjugate transposed of something to the power m, that's the same as doing it first. So you can do this term by term, and this gives you the desired result. So in the end, we end up with a matrix exponential that's defined for all kind of matrices. And then you can show, that's the last thing I'm going to show theorem for any x, no, sorry, for any a in the complex numbers, there is an x in the matrices such that a is the image of this exponential. So if you have a complex matrix, then you can always write that as the exponential of some other matrix. It's not unique, but you can always do it. But whereas for a real matrix, you can always write it as the image of a complex matrix, but not necessarily as the image of a real matrix. Just like -1 can be written as e to the to I pi, so you can get -1 out, but you have to use a complex number. Real matrices are not necessarily the exponential map of a real of another real matrix. And again, it's the same argument in it sort of mirrors the fact that the thing we have in dimension